And the next speaker is Parhi, who is a professor at the University of California, San Diego. His PhD at École Polytechnique.
Postdoc with
PhD,
Michael Unzer.
yeah. Thanks for the introduction and thank you for inviting me to speak. So today I'll talk about kind of some differences between global and local minimizers in neural network optimization problems. And this is joint work with Tongtong Liang, Dan Chao, and Yuxiang Wang at UCSD. Tongtong is a PhD student who works with me and Yuxiang, and he did all the hard work for this project. Okay. So as everyone here knows, the world is now based on neural networks, LLMs, ChatGPT, all that fun stuff. I guess GPT-5 came out like a week ago and no one liked it, which is kind of funny. So I think this article's from Friday, I guess. So on that note, maybe it's a good question to ask, do we even understand how neural networks work? Today I won't talk about any large language models or large models for that matter, but at least for some simple models like single hidden layer neural networks, we can see some kind of interesting results. And sort of one of the principal outstanding problems in neural network research is even just understanding why do neural networks generalize. You can ask a lot of questions that skirt around this issue, what is the role of regularization? What role does the training algorithm actually play? What role does the geometry of the loss landscape play? Because these are very, non-convex optimization problems. There's lots of basins, lots of local minima, lots of global minima. So today we'll kind of, circle around these three questions, focusing on shallow ReLU neural networks, so one hidden layer. And we'll sort of look at two case studies, the first being global minima, which I'll associate with low norm solutions, meaning those trained with weight decay. And then we'll look at local minima, associating those with solutions that are stable or flat in some sense. In particular, for these local minima, these are the ones that solutions that gradient descent can stably converge to, kind of from the dynamical systems perspective, and this perspective is kind of motivated by some recent sort of edge of stability phenomenon. So what we'll see today is that there's this sort of separation between these two kinds of solutions, which I think is quite interesting and also tells us we really don't know what's going on. So part one of the talk will focus on low norm minima, and then part two will focus on flat minima. Okay, so part one of the talk. So the mathematical formulation we're going to take for the whole talk is that we're interested in analytic properties of trained neural networks. So neural networks are drawn with these funny diagrams, but they're just functions actually. So I put in some input x, it lives in RD, for example. Out I get some f theta of x, so I'm interested in looking at properties of this function mapping actually, and theta here is just a collection of all of the parameters in the network. So now if you want to actually train a neural network, you have some data set, xy pairs, and then you're looking at optimization problems like this. So here we're minimizing over our vector of parameters theta. We have two terms, a data fidelity term, and here I've written an explicit regularizer. For some of the talk we'll have that, for some of the talk we will not. So this is Tikhonov regularization, or what people in machine learning like to call weight decay, because give new names to old ideas, but whatever. And then again, what we're going to focus on today is really understanding properties about the end-to-end mapping of the functions realized by neural networks. And something interesting that happens when you actually use weight decay in neural networks is this sort of balancing effect. So here's one neuron in some deep neural network architecture. It has some set of input weights W and some set of output weights V. So this blue circle here is just the ReLU activation function. So if I take some input Z to this neuron, out I'll get something that looks like this. So I take Z, I weight it by W, so that's W transpose Z. I take the positive part, that's the ReLU, and then I multiply it by the output weight vector V. So that's just the mathematical expression for a single ReLU neuron. And then again, when you're training with weight decay, it just means you add this L2 penalty to your objective. And then what's interesting is that if you take a deep neural network of any architecture you want and you train it with weight decay and pretend you can find a global minimizer, then it turns out that the two norms of the input and output weights are necessarily balanced. So written explicitly, it just means that the norm of W equals the norm of V. Okay, so why do they call it weight decay when we're trying to solve optimization problems that look like this? Well, if we write down the gradient descent update on theta I, it's going to look something like this. So eta here is the step size or learning rate. And then if I rearrange terms a little bit, I get something that looks like this. So here's just the gradient descent update on the data fitting part of my objective, and now I just have a small constant times the current iterate, so that's just the step size times the lambda in my actual regularizer. And this is what people call weight decay, because at every iteration of gradient descent, you're essentially sort of decaying the weights. So people call this the weight decay objective for that reason. Okay, so then coming back to this whole neural balance idea, it's not a very complicated thing, actually. It's just happening because the ReLU is a homogeneous function, which means I can just scale up the input weight W by some positive factor gamma, scale down the output weight V by the exact same factor, and then the function mapping of this neuron remains unchanged. And this is exactly why at a global minimizer, the norms of these two guys are equal. And the proof is actually just one line. Essentially what this optimization problem is capturing is that the data fitting part of the loss isn't going to change if I add in all of these scalings. So I'm really just asking, how do I make the L2 norms of all of my weights as small as possible? And if you take the derivative of this guy, set it equal to 0 and solve for gamma, and then plug this gamma back in, you'll find that the weights have equal magnitude. So what this also means then is that a global minimizer, the sum of squares of the weights also kind of equals this product form of the weights. It's not a new idea either. I think this goes back to 1998. There's probably earlier references. If anyone knows any earlier references, please let me know. And then kind of became popular sort of 2015 onward. Question, yeah.
This doesn't depend on the fan-out degree as long as you're looking at those weights.
Yeah, as long as you're looking at it, like any neuron that is like this, it holds. Or any even homogeneous layer too. So like linear activation functions as well, same thing happens.
I was thinking like, usually like after graduating, like you take output,
Yeah.
Like, but if there's no, it's not counted as a weight, then something like this won't happen.
I don't think I quite understand your question.
Like basically there's no V, like I just take down.
Oh, sure, I guess if there's no V, I mean, yeah, but then like, if you're in some layer of a deep neural network, there's a V that comes right after anyways. And like that V and that W will have equal norm. Does that make sense? Cool. Any other questions? Okay. So then this reveals that weight decay is actually secretly a sparsity promoting regularizer, even though it's, it looks like L2 regularization on the surface. And here and onward in the talk, we'll now specialize to one hidden layer neural networks with scalar outputs. So these are just functions that look like this. And here I am going to include biases. So I have a linear combination of neurons. These are these W transpose X minus Bs, and then the positive parts. And then I have my second layer weights, which are these Vs. And theta here is going to denote all of the V's, W's, and B's. So, here's my objective where I'm trying to, train my neural network with weight decay. By this whole neural balance thing, it's actually equal to this regularizer where you're looking at the sum of the products of the weights. And then I can do another trick, actually, and I can absorb the magnitude of the input weights into the output weights because the ReLU is, again, homogeneous. And by just adding this extra constraint here that the norm of the W's are 1, I can actually consider this regularizer here. So again, this is weight decay. This is what people like to call the path norm regularizer. And then this is actually just the regular old lasso for this problem, but just note this is a non-convex optimization problem, so it's kind of like a non-convex lasso, but you are promoting sparsity sort of at the neuron level because of this regularizer. These three problems are all equivalent also, so I can take any solution to the bottom two problems, just rebalance the weights, and I'll get a solution to the original weight decay problem, so it's okay to sort of think of these all as equivalent problems. Okay, cool. So now we kind of have the general setup. And now we're going to move to function spaces so that we can actually study the end-to-end mappings of these neural networks. So let's consider this space right here. These are just finite width neural networks, and I'm letting the width be any natural number. It turns out that the path norm actually is a valid norm on this space, but the space actually isn't closed. So if I take its appropriately defined completion, this is actually going to be a Banach space. In particular, it's the Banach space of functions where I can write all the members as essentially integral combinations of neurons. This measure nu here is just playing the role of the output weights now. And these spaces are often called variation spaces, so that's why I'm denoting it by this mathcal V. So this formulation goes back to the sort of foundational work of Andrew Barron in the 90s, and then I think Francis Bach kind of popularized it a bit later. So we're going to sort of adopt this perspective when studying neural networks. Cool. Okay, so we have these variation spaces, and it turns out they're actually very related to spaces of measures, which is, I guess, obvious because these functions are integral combinations of measures. So we have a function in V. It has this integral representation as an integral combination of neurons, and it has some norm, because I told you it's a Banach space. Since every function in the space is parameterized by a measure nu, it turns out that the norm on this space is actually the total variation of the measure that's associated with the parameterization. So that's why this is a Banach space. What this really means, though, functionally, is if I have a finite width neural network, its variation norm is just the path norm. So just kind of keep that in mind as the prototypical example. Furthermore, this also then means that the variation space is isometrically isomorphic to the space of measures, which then lets us prove a lot of interesting results. Yes?
So far, how many layers do your neural networks have?
So today I will only talk about one hidden layer because I want to prove theorems that are nice. If anyone knows how to go deep, please talk to me later. Question?
So because you're defining the norm as this path
Yes.
norm, and that derivation came from the fact that it was the minimizer of this loss function with weight decay.
Yes.
You're saying that this norm is valid for only the minimizers.
No, so this norm is valid for any finite width network. Yeah. If I used the weight decay one, it would only work, at the minimizers because of the balancing thing. But here, because I'm actually using the path norm instead of the weight decay, so this is maybe the trick that makes everything work. So like, parameter space wise, we're like, okay, weight decay is the same as the path norm thing. The path norm thing has nicer properties, so let's use that to sort of build this Banach space. Yeah.
Got it.
Cool. Question?
I may be missing something, sorry, but it's for two-layer networks.
Yeah.
This is just L1 norm.
Yeah, you can think about it that way, yeah.
So why do we need to call it? So can we just think of? Yeah.
So yeah, you can think about it like the L1 norm, but like a finite width neural networks, this nu is a sum of Diracs. Diracs technically aren't functions, so you should write M norm there, but if you want, you can think about it like a capital L1 norm. If you're okay with Diracs being in L1, yeah, if you want, yeah. Cool. Okay, so with this then, you can prove something that's maybe a bit obvious and actually goes back quite a while, is that now if you want to optimize over this function space and you want to do some data fitting plus regularization, and your regularizer is just the norm in the space, then there always exists a solution that's actually sparse in the sense that the number of neurons is bounded by the number of data. So this really does go back to this work of Zuchowski in the 1940s, and then many other people following up on it. So what this means, though, is that if I'm training a sufficiently wide neural network, meaning my width is at least the number of data, with weight decay to a global minimizers, then every one of those guys will actually be a solution to the Banach space problem. Said differently, the kinds of functions that neural networks learn are the ones precisely in this space V. So all of this stuff then lets us set up the function space viewpoint to actually study neural networks, because essentially now we have this chain of equivalences. We have weight decay is kind of equivalent to this path norm regularized problem, which is then kind of equivalent to this problem we're optimizing over V if we're in this sort of sufficiently wide scenario. And this then allows us to basically move all of our efforts to function space, which is actually quite a bit easier than trying to study things directly with the parameterizations of the neural networks. Is the setup of everything clear? Cool. Okay, so then you can ask, how well do weight decayed networks actually perform? So one possible way you could measure this performance is the sort of non-parametric function estimations perspective. So here, we can suppose our x is our IAD uniformly, say, on the unit ball of Rd, and suppose we see y equals f of x plus noise, where f actually lives in this variation space. In that case, you would be interested in trying to bound something like the minimax risk for this function class, meaning we'd want to look at a quantity like this. So we're taking an inf over all estimators of our data, soup over our function class, and then we're looking at this mean squared error quantity. So this is one way we can look at the performance of our neural network estimators. We can also look at it from more of a statistical learning perspective as well, supposing that the x's and y's come from some distribution p, and if we let r of f denote the population risk with the squared error loss, and let r hat n be the empirical risk, then another quantity you could be interested in bounding is the generalization gap, which is just the difference between the population risk and the empirical risk. So we'll look at how these two quantities behave first for these weight decayed neural networks, and then later we'll talk about flat minima and local minima. And all of this stuff essentially hinges on approximation theory for these variation spaces. In particular, it holds that if someone hands you a function in V, then there exists a finite width ReLU network with k neurons such this L infinity error taken on any compact domain omega of Rd has a decay rate that looks like this, so k to the minus 1/2 minus 3 over 2d. So this rate does again go back to this famous work of Barron. In particular, the L infinity approximation is really due to Matuszek in 1996. So then by Karl's inequality, this actually then directly gives us a bound on the metric entropy for the unit ball of this Banach space. So just to give some context to these exponents, if this one is minus alpha, this one is just minus 1 over alpha. And the main takeaway here from this is that the approximation rates and entropy numbers don't actually grow with input dimension d, so that's kind of interesting, and this will play a role when we look at the statistical rates that we study. Cool. Okay, so now we can talk about the minimax risk question.
So can you comment on that, like the contrasting it with, say, RKHS,
Yeah, so like I guess with RKHSs, and if you want to kind of concretize them with L2 Sobolev spaces, so you're in like HS, but the only way to be in RKHS is S is greater than D over 2. So there, even though it looks like your entropy numbers are kind of suffering poorly with dimension, just so that you have point evaluations making sense, you need a lot of smoothness. And in particular, I won't talk about this today, but like the sort of largest RKHS you can have is this sort of HD over 2 space. It actually embeds into V, and V is actually slightly larger. Yeah. Okay, so now we can talk about the minimax risk. So let's suppose that, again, our x's are drawn IID uniformly from the unit ball of Rd, and then we see y equals f of x plus noise. Then any solution to this weight decay objective problem actually satisfies this decay rate right here. So the mean squared error decays like n to the minus d plus 3 over 2d plus 3. This is actually the minimax rate for this class, so no other method can do better, so that's kind of interesting. And we have this n to the minus 1/2 rate, so in some sense there's no curse of dimensionality. Maybe what's more interesting, though, is that linear methods, such as kernel methods, or if you use a neural tangent kernel or something, actually necessarily suffer the curse of dimensionality for this function class. So we also proved this linear minimax lower bound for this class, where you have this n to the minus 3 over d plus 3. So the d in the denominator of the exponent there is precisely the curse of dimensionality. So that's cool. We can also then talk about the generalization gap. Yeah?
It can be a constant.
Yeah, so lambda scales with n. I would have to double check how it actually scales, but yes, lambda is not a constant. It depends on the number of data. Yeah. Yes.
So just one comment. It's like, so you assume you're in a complex set, but you think
Yes. So this is L2 of like the B1D.
So what happens near the boundaries of that domain?
So here the boundary isn't actually going to play a big role because of how the variation space is defined. So even there, essentially, even if you have a ReLU very close to the boundary, it still sort of has a norm of 1. But later, when we talk about flat minima and local minima, the boundary is actually going to play a very interesting role, which will make the rates be more weird. Yeah. Okay. And then just kind of quickly, we can talk about the generalization gap then. So here, again, we'll assume our x's and y's come from some distribution, and just for technical reasons, we'll suppose that this measure p has compact support. Then you can show with high probability any solution to this problem. Here, again, the weight decay objective problem has a generalization gap that decays something like this. So again, sort of a dimension-free rate for the generalization gap. Okay, so that's kind of interesting. So maybe you want to say that like low norm solutions or low norm global minima generalize in the sense that this generalization gap goes to 0 as n goes to infinity. And then maybe you want to say that low norm solutions also generalize well because this rate doesn't depend on input dimension. The story will be very different for local minima that are flat. And that's kind of important because like this whole setup here isn't very realistic. One, like we're regularizing, oftentimes people don't regularize apparently. Two, we're assuming we can access a global minima to this very non-convex problem. So, maybe we can never even find such an estimator. So in part 2 of the talk, we're now gonna kind of, relax all of the assumptions we made in part 1, trying to make the scenario a bit more realistic to understand what's really going on with generalization. And the way we're going to do this is looking at local minima that are also flat. Yes?
Part of being using the exact minima
Yes.
was just equivalence between the path norms
Yes.
and
Yes.
L1 norms.
Yes.
And that was due to the fact that it's a balance condition.
Yes.
Does that happen in practice? Do you
So
actually get this balance?
empirically, we've seen if you do explicitly regularize with weight decay and train really long, yes. So we do. There's actually many papers, not just ours, that have observed this balancing thing happening. So it's not unrealistic, I guess.
Well, like, I guess it's like 2 separate things, right?
Yeah.
You could have the balance condition and not actually get sparsity.
Oh, this is true, yeah. And then I guess something else that we've seen though is if you actually train like 4 times longer than you think you should, the sparsity actually does start to decrease. Yeah.
But you're saying the balance condition happens before that.
Yeah. Okay, so now we will migrate to part 2 of the talk. And the way we're kind of going to look at this is really focusing on the loss landscape geometry. So like I said before, is like the loss landscape for neural network training problems is very non-convex. And again, people often don't explicitly regularize, so they're relying on this sort of implicit bias of gradient-based training. So really, they're looking at optimization problems that look like this. So here, there's no regularization, and I'm just doing least squares loss over neural network parameters, trying to fit my data of XY pairs. So then, you can ask, like, what is, kind of the mechanism behind generalization in neural networks if this is the optimization problem we're actually looking at? There are many stationary points to this problem. Like, what is kind of the role of geometry, or does geometry actually play a role for generalization in this context? So this kind of then goes back to 1997. There's this paper from, Jürgen Schmidhuber, the legend himself. The title was just flat minima. And here what they were essentially saying is that, if you actually try to look for flat minima, these are going to outperform everything else you could, hope to do. So like, just stealing the pictures from their papers, like, if we're looking somewhere in our loss landscape, if we have a very wide basin around a global or local minima, they're saying that this one should be better. Meanwhile, if we're at one that's much more sharp, we're probably going to perform worse. So again, this is 1997. There has been some recent resurgence on this topic. Let's, maybe migrate, I guess, 20 years forward. There are these 2 papers at ICLR. There's also this paper at ICML. So maybe just to quickly summarize what these 2 papers were saying is like, these 2 are kind of on the side that like, it's sort of well known that sharp minima lead to poor generalization, while flat minima actually generalize well. But then this ICML paper is kind of more interesting because it says that most notions of flatness are actually problematic to explain generalization, and then they prove something kind of interesting is that if someone hands you a neural network that generalizes well in their sense of well, you can construct one that corresponds to an arbitrarily sharper minima that has the same generalization performance. So then you can start asking like maybe what's actually going on, and like what is actually the role of flatness in all of this. Moving forward, I guess then 5 more years, I guess sharpness aware minimization, or SAM, came out in 2021. There's also this kind of interesting paper in 2020 about understanding generalization through visualizations. And these 2 papers are still on the side that flatness is good. The second paper is kind of interesting because they have some nice pictures. So here they're trying to do binary classification on this data set right here. On the left, this is a decision boundary we would probably want. and then they plotted what the landscape looks like around that minima, and it looks very flat, very wide basin. And then here's another zero loss solution on the right. We probably don't want this one because it's probably, it will generalize poorly. And then they plotted what the landscape looks like around this minima, and this one looks very sharp. So, okay, so maybe maybe flatness does have some role to explain generalization. Something else that's, I guess, important is that large basins are also more likely to be found by gradient-based training. So if we can understand if having a large basin or a flat minima is good, then we could even possibly hope to find these minima with gradient descent. Again, so now theoretical insights for this phenomenon are starting to emerge. So, Dima, Mariam, and Zaid here had this paper recently about flat minima generalizing well for, matrix sensing type problems. There's also some interesting work from Daniel Sodry's group the last few years where they're sort of trying to incorporate the actual gradient descent algorithm into the analysis as well. So they're taking this perspective of minima stability actually and saying like, okay, gradient descents of dynamical systems, the minima that are sort of stable in this dynamical system sense are also then related to flatness. So this is kind of a nice theoretical framework. And I guess maybe one caveat or remark I'll make about all of these prior works, though, is that they do often focus on being at a global minima and then trying to look at the flat ones. But there's increasing theoretical evidence that if you're using gradient descent actually with large step sizes, you'll never actually hit a global minima. So then what we did anyways is that we sort of took this framework from these bottom two papers and then focused on like extending it beyond this interpolation scenario and then also studying the statistical properties with like minimax risk and generalization gap. And the basic idea behind all of this is basically linearizing the gradient descent dynamics so we can actually study them. So again, we're looking at this objective here, just least squares loss, non-convex optimization problem. Again, if we write down the gradient descent update on theta, it looks like this, eta again being the step size or learning rate. Again, like directly analyzing this is kind of hard, so maybe let's linearize the dynamics. Let's take the Taylor expansion around some point theta 0. This is just the second order Taylor expansion here. With this, I can then look at the linearized dynamics about a point theta 0, and I'll get an iteration that looks like this. So all I did is I took the gradient of this Taylor expansion and plugged it in for the gradient in the above iteration to get the below iteration. Yes?
Are you looking at solutions like around zero loss solutions?
No, so we're going to look at any stationary point. If you wait another
so
slide.
Can be negative.
Yeah. So near, So near this point theta 0, this is going to well capture what gradient descent is actually doing. So then this is this whole idea of minima stability. So this definition we pulled from these two papers is that if theta 0 is some stationary point, let's call it theta star, then given epsilon greater than 0, this stationary point is said to be epsilon linearly stable. If essentially if we're near this minima, if the iterations ever enter near the minima, we're never going to leave. So we're essentially getting trapped around the minima. So this is what you would call epsilon linearly stable. And this is actually very tightly linked to flatness, actually. It's actually the same thing as measuring flatness of the loss landscape. So this is a nice lemma from this Mulyaev et al. Paper, is that for any epsilon greater than 0, a stationary point theta star is epsilon linearly stable if and only if this lambda max of the Hessian of the loss at the point is bounded by 2 over eta. So this here is exactly just capturing the sharpness of the landscape geometry. And again, to remind everyone, this eta here is the step size or learning rate for our gradient descent iterations. Yes?
There is a positive definiteness condition as well, because if you're near it,
Yeah.
if theta star is a saddle point, it'll tend to run away with the gradient.
So this is because we're linearizing the dynamics. So this result is for the linearized dynamics. So I guess for vanilla gradient descent, this would happen. But because we're looking at these linearized dynamics, I think that's why they could get this result.
If theta star were a saddle point, and the Hessian there had negative eigenvalues, and you started within some neighborhood of that, it would not have this attraction property that you're talking about.
That's a good question. Maybe we can check out their paper during the break, because that's actually a very valid point, and I don't have a good answer right now. but let's roll with this for the time being. So essentially what this shows is that large step sizes are essentially related to having flatter minima, and this is actually the sort of idea that this Chow et al. Paper ended up using to show that, unless your step size is sufficiently small, you're not actually going to end up interpolating your data. So with this then, we decided to define this class we'll call theta flat of eta, which is just a subset of all of our neural network parameters where we have this bound on the Hessian, and we're going to analyze properties of neural networks that are realized by this subset in parameter space to prove our results. And again, these are, in some sense, the solutions that gradient descent with step size eta can actually stably converge to. Okay, so what's interesting about this class, this subset of the neural networks, is that the stability or flatness constraint is actually imposing a data-dependent regularization. So again, here's our one hidden layer neural network. If someone hands us a theta in this flat class, you can actually end up showing that this quantity here is bounded by 1 over eta. This g here is a weighting function that sort of implicitly depends on the law of the x's. I won't get into the details during the talk. But if you stare at this for a second, this is actually just a weighted path norm, which is interesting. So what we're seeing is that step size is implicitly controlling the regularity of the solutions. And then as step sizes get very large, you're sort of favoring neural networks that are just the zero function, essentially. So with this weighted path norm, we can then play the same game we played earlier of doing this whole completion story and looking at this set of finite width neural networks. Now the weighted path norm is also a valid norm on this space. So I can take its appropriately defined completion. I can get a Banach space of functions that have these integral combinations. I'll call the completed space now V sub g because it's weighted. Because now the norm on the space isn't just this L1 type of norm on the measure, but it's weighted by this function g. And luckily, with the paper with Rob and collaborators at Texas A&M, we already developed the approximation theory for these sort of weighted variation spaces. So we can actually use a lot of those results to study properties of these flat solutions like the minimax risk and generalization gap.
So I know
Yes?
you're not going to say anything about G, but I mean, obviously.
So for the uniform,
negative,
so yeah, it's non-negative and it's sort of decaying near the boundaries. For the uniform distribution, I'll write down what it is explicitly on the next slide, but again, it depends on the x's. Yeah. Okay, so again, now we can look at the minimax risk. So let's suppose our x's are IID uniform on the unit ball. In this case, you can actually show that G essentially looks like this, 1 minus b to the power d plus 2. So if you have a ReLU near the boundary, this is actually going to penalize it not very much compared to a ReLU that's sort of near the middle. And again, we'll be in this non-parametric regression scenario where we see y equals f plus noise, f of x plus noise, and now f is going to be in this weighted variation space, v sub g. So now if someone hands us one of these flat solutions, what we showed is that an upper bound on the minimax on the risk looks like this. So it's this messy exponent. I won't read it, but you can stare at it for a second and see that this actually is suffering the curse of dimensionality. We also proved a lower bound for this class of functions, which looks like n to the minus 2 over d plus 1. So for this class of functions, the curse of dimensionality is in some sense necessary. Maybe this isn't super interesting, though, because it just means v sub g is a hard class of functions to learn. So we can then also look at the generalization gap as well. So here we'll suppose that x's and y's come from some distribution p. Here we do, for technical reasons, need to assume the x distribution is uniform, and then the y distribution, again, has to just be bounded. Then you can also show with high probability any solution in this flat class will satisfy this generalization gap bound right here. So once again, you see that this rate suffers the curse of dimensionality. And then we were wondering, like, is this actually necessary? This is a big mess to read, but essentially what we showed is uniformly over this flat class, if we inf over all risk estimators, which is what this R tilde is, then we have this lower bound as well for the generalization gap, which is n to the minus 2 over d plus 1. Yes?
I apologize. I'm very confused about this theta flat class
Yes.
because it feels like if we do some rebalancing, like
Yes.
you mentioned, you can take any theta and find an equivalent point in theta flat.
So yes, so this is true, but I guess it doesn't contradict these results though.
But then I guess this is like a statement about any solution, like any point in parameter space, since any point can be mapped.
No, oh, I see. Okay, I think I see the confusion now. So if you do this rebalancing thing, where is it? So in this flat class, we have a bound on the radius essentially. So if you do this rebalancing thing, you'll leave the flat class.
Sorry, where's the
This two radius.
But isn't this a bound on the maximum item?
This is, yes, this is correct. But then what this is implicitly controlling is this weighted path norm with this similar bound 1/8. So if you do this rebalancing, you're going to not be in this flat class anymore.
Okay, maybe I need to do my algebra more carefully.
Sure, sure. Thanks. Good question, though. Good question. Okay, so then I guess maybe then the takeaway from this result is then flat minima generalize in the sense that this rate does go to 0 as n goes to infinity, but maybe you would say they don't generalize well because of this interesting dependence on dimension. So then maybe just to quickly wrap up, I think there's some interesting kind of non-parametric statistics stuff that came up when we were doing this analysis, in particular constructing the hard functions for the lower bound. So again, for the uniform distribution, we can think about this weight function here, which I said means that if your ReLU is very close to the boundary, it won't get a very large penalty. So again, this is a ReLU function. It has some activation threshold. What this means is that the functions that are hard to learn are precisely the ones that are sort of pushed to the boundary, which I'm trying to depict with these two figures. So these are actually the functions we use for the lower bounds for both the minimax risk and the generalization gap, which is, I guess, quite a bit different from the usual bump function constructions you do in non-parametric statistics for lower bounds. So I think just from that perspective, this is also just an interesting kind of tool, if you want. So just to quickly summarize then, what we saw is that low norm solutions and flat solutions both generalize, but maybe you would say low norm solutions generalize well, while flat solutions in some sense suffer the curse of dimensionality. So there's this kind of exponential separation between these two kinds of solutions. So maybe the main takeaway I'd want everyone to take from this talk then is maybe flatness isn't the sole explanation for generalization in neural networks. So there's so many moving pieces. You know, there's gradient descent dynamics, there's loss landscape geometry, all of this stuff. Like understanding their interplay, I think, is quite challenging. And I think the results I showed here kind of further that point that we really don't know what's going on. Papers on archive, we put it up like, I guess, a month-ish ago. And if there's any other questions, I'd be happy to take them now.
Yeah, so I was wondering if we restrict attention to points where you have zero loss also.
Okay.
Then one can argue that the stationary points will all be local minima.
True.
It hits
True.
zero loss. And one can argue that in a lot of neural networks,
Yeah.
we're actually interested in zero loss
Sure,
solutions
sure.
because we have over-parameterized. Can then you say something more in that
I mean,
case?
these results do hold for any stationary point. So
But does it get better if you know already?
yeah, that's a good question. I'm not sure if we have that extra information, can we say something slightly stronger? So this is a good question, actually. I'm not sure. Yeah.
Thanks.
Yeah. Yes.
Yeah, I have a question. So, like, can you characterize the kind of imbalances or approximate imbalances associated with this weighted variation spaces? Like, you know, and I'm trying to draw an analogy with RPHS and, you know, translation invariant.
So I mean, first of all, it's clearly not translation invariant because of the weighting function. But then even, I guess, rotation invariance isn't even there either. It's because, I mean, because it's so intrinsically tied to the geometry of the domain, these function spaces, I think you have very few invariances.
Flatness is clearly associated with like robustness and perturbation.
Yes, this is true. This is true. So yeah, there's.
So like how can you reconcile?
Yeah, that's a good question, and I don't have a good answer right now. Yeah, but it's a good question. Thanks.